Welcome to Sleepy Science Stories, where we drift through the universe in quiet wonder, exploring the mysteries that surround our tiny world. Tonight, we turn our attention to a traveler from beyond our solar system, an object astronomers call 3I Atlas, the third confirmed interstellar comet ever discovered. Many people have asked a simple question: is this interstellar visitor a threat to Earth? Let us settle our minds, breathe deeply, and explore the science together, calmly, slowly, and clearly, so we can understand what this cosmic wanderer truly means for our planet and for our place in the universe. Now, let us begin our gentle journey. 3I Atlas, a visitor from beyond. There is something moving through our solar system, something ancient and silent, traveling across distances so immense that the human mind can barely grasp them. This is the story of 3I Atlas, an interstellar visitor that did not form here, did not belong to our sun, and has crossed the deep dark between stars to arrive in our cosmic neighborhood. It is only the third confirmed interstellar object ever observed by humanity. A discovery built not on dreams or speculation, but on hard measurements, spectroscopic analysis, and precise orbital calculations. Astronomers across the world have traced its path and studied its light. What we know comes from data, from instruments, and from science practiced with patience and care. 3 Atlas has challenged our expectations from the moment it was detected. It releases a compound called nickel tetracarbonyl, a substance never before seen occurring naturally in space. On Earth, it is associated with industrial processes. Telescopes have measured this emission at several grams per second without iron present, defying established models of comet chemistry. Then there is its motion. The trajectory of this object lies within Earth's orbital plane in a way that should occur by random chance only very rarely. It makes unusually aligned close passes with Venus, Mars, and Jupiter, events that, when considered together, form a chain of improbabilities not easily explained by chance alone. For those who come seeking clarity, not fear, let us move forward gently. We will follow the evidence step by step, guided by observation and mathematics, not by alarm or imagination. Physicist Avi Loeb, known for challenging assumptions about our first interstellar visitor, has noted that this object presents multiple independent anomalies. He has suggested a significant probability, between 30 and 40%, that its nature may not be entirely natural. These ideas are not drawn from speculation, but from anomalous measurements observed at professional observatories. There is a jet pointing toward the sun, behaving unlike typical comet outgassing. There are nickel emissions consistent with refined industrial profiles. There are orbital alignments that strain chance. And as it travels through our inner solar system, we cannot observe it for a period of time while it moves behind our star, a brief blackout in our watchful gaze. When it emerges once more, the scientific community may finally uncover its true nature. For now, we simply watch, wait, and measure. A quiet visitor passes through our skies, and in its wake, it leaves questions older than our species, stretching into the dark between stars. Let us continue this exploration, slowly and calmly, as we seek to understand what an interstellar traveler can teach us about ourselves, our world, and the vast, silent universe that surrounds us. Chapter 1: The Object That Shouldn't Be This Massive. In late September of 2025, a scientific paper appeared on the Arxiv preprint server. Its title was unremarkable, technical, the kind of document that normally draws attention only from specialists. Astrometric and photometric analysis of interstellar object. 3I Atlas. The paper detailed observations compiled from 227 observatories worldwide. More than 4,000 individual position measurements, taken carefully across 3 months of patient watching. Inside that technical analysis was a number that changed everything: 33 billion tons. That is the minimum mass of 3I Atlas, calculated not from direct measurement. We cannot weigh objects as they drift through space, but from the absence of something we should be seeing. Non-gravitational acceleration. When comets venture close to the sun, ice on their surface sublimates. It transforms directly from solid to gas without passing through liquid form. That gas jets away into space, and as it does, it acts like a tiny rocket engine, pushing against the comet, changing its trajectory in measurable ways. Astronomers call this non-gravitational acceleration, and it is one of the defining characteristics of active comets. We can detect this effect by tracking a comet's position over time and comparing where it actually is to where pure gravity says it should be. If the comet arrives ahead of schedule or behind schedule, or drifts to one side of its predicted path, that tells us that outgassing is pushing it around, altering its course. 3I Atlas shows almost none of this. Its trajectory matches a purely gravitational path to within extraordinarily tight margins. The upper limit on its non-gravitational acceleration is less than 15 meters per day squared. For an object actively releasing gas, and we know it is releasing gas because multiple telescopes have measured the outflow directly, this is vanishingly small. The only explanation consistent with what we observe is simple. The object is so massive that the thrust from outgassing barely moves it at all, like trying to push an aircraft carrier with a garden hose. The force exists, but the mass is simply too large for the acceleration to be detectable. So the astronomers worked through the mathematics. Given the observed gas loss rate of approximately 150 kilograms per second, measured by the James Webb Space Telescope on August 6th, and given the absence of detectable non-gravitational acceleration, what is the minimum mass this object could possibly have? 33 billion tons. If you assume it is made of rock and ice with a density similar to other comets, somewhere between 0.5 and 0.9 grams per cubic centimeter, you can calculate a minimum diameter. The answer emerges as more than 5 kilometers, possibly significantly more, depending on its internal structure and composition. For context, the two previous confirmed interstellar objects were both quite small. Oumuamua, discovered in 2017, was perhaps 200 meters across at its widest point. Borisov, discovered in 2019, was probably less than a kilometer in diameter. Both were modest chunks of material, exactly what you would expect for debris ejected from distant planetary systems during their formation. 3I Atlas is 3 to 5 orders of magnitude more massive than either of them. That means it is 1,000 to 100,000 times heavier. This creates a statistical problem that is difficult to resolve through natural explanations alone. Objects in space follow what mathematicians call a power law distribution. For every large object, there are exponentially more smaller ones. If there is one rock 10 kilometers across wandering through interstellar space, there should be hundreds of 1-kilometer rocks, thousands of 100-meter rocks, millions of 10-meter rocks. The numbers explode as you move towards smaller sizes. This pattern appears everywhere in nature. It is how crater sizes distribute themselves across the surface of the Moon. It is how earthquake magnitudes arrange themselves on Earth. It is how asteroid populations in our own solar system are structured. Big things are rare, small things are common. The universe does not manufacture as many mountains as it makes pebbles. Based on models of planet formation and estimates of how much rocky material gets ejected from star systems during planetary development, astronomers can calculate roughly how often we should expect interstellar objects of various sizes to pass through our solar system. For something in the 5 to 10 kilometer range, the expected rate is approximately once per 1,000 years, perhaps once per several thousand years, depending on assumptions about the density of interstellar material and the efficiency of planetary formation processes. We have been systematically searching for interstellar objects for roughly a decade. 1 decade of looking, and we found one of the rarest size classes possible. Avi Loeb has described this as the mass budget problem. There simply is not enough rocky debris floating around in interstellar space, at least according to our current models, for us to be finding massive objects this quickly, unless either our models are fundamentally wrong, or this particular object represents something other than random ejected planetary material. But there is another interpretation of the 33 billion ton measurement. one that requires thinking about mass in terms of structure rather than bulk material. If you were designing a vehicle capable of traveling between star systems over millions of years, you would not build it as a solid chunk of rock. That would be impossibly heavy, requiring enormous energy to accelerate and decelerate. You would build a shell, a thin structural framework with vast empty interior volume. That is how every long-distance vehicle humanity has ever constructed works. From ships to aircraft to spacecraft, we achieve strength through geometry, not through bulk. A hollow sphere 10 kilometers in diameter with walls a few hundred meters thick could easily weigh 33 billion tons. It would have enough mass to resist perturbations from surface outgassing, especially if that outgassing were controlled, directed in specific ways to maintain rather than alter the trajectory. This is not proof of anything. It is simply another way of looking at the same number, the same 33 billion tons, through a different conceptual lens. Mass as structure rather than mass as material. The observations permit both interpretations. Which one is correct depends on information we cannot yet obtain from telescopic observation alone. Chapter 2. The chemistry that shouldn't exist. On August 6, 2025, the James Webb Space Telescope turned its infrared sensors toward 3I Atlas. What it detected was something that should not exist in nature. Nickel tetracarbonyl, a compound with the chemical formula nickel bonded to 4 carbon monoxide molecules. This substance is not found in natural environments. On Earth, it exists only as a product of industrial processes, specifically the Mund process for refining nickel from ore. The Very Large Telescope in Chile confirmed the observation. 4 grams of nickel tetracarbonyl per second, streaming away from the object, and notably no iron present in the emission signature. In nature, nickel and iron almost always occur together. They form together in stellar nucleosynthesis. They condense together in protoplanetary disks. They appear together in meteorites and asteroids. Finding nickel without iron is like finding thunder without lightning, possible in principle, but so rare that it demands explanation. Nickel tetracarbonyl forms only under very specific conditions. It requires nickel, carbon monoxide, and a particular temperature range, usually around 50 to 100 degrees Celsius. Too cold, and the reaction does not proceed. Too hot, and the compound decomposes back into its constituent elements. The temperature zone where this molecule can form and remain stable is narrow, and it happens to be exactly the temperature range you would find on the surface of a comet at approximately 3 astronomical units from the Sun, roughly the distance where 3I Atlas was when these observations were made. This is where the puzzle deepens. Yes, the temperature is right, but where does the pure nickel come from? And where does the carbon monoxide come from in sufficient quantities to produce this reaction at a rate of 4 grams per second? Comets do contain carbon monoxide frozen into their ice matrix. As they warm, that carbon monoxide can sublimate, turning directly from solid to gas, but pure metallic nickel on a comet surface. That is far less easily explained. One hypothesis suggests that the object might have an unusual composition, perhaps enriched in certain metals due to the conditions in its parent star system. Different stars have different metallicity profiles based on their formation history. A planetary system that formed from material already enriched in heavy elements might produce debris with unusual chemistry compared to solar system objects. Another hypothesis proposes that we are seeing evidence of differentiation. If the object was once part of a larger body that underwent heating, sufficient to melt and separate into layers with heavy metals sinking to the core and lighter materials rising to the surface, then perhaps what we are observing is a fragment of that core layer exposed by some ancient collision. The nickel tetracarbonyl would then form from the reaction between that metallic surface and carbon monoxide in the outgassing ice. Both explanations are possible. Both require specific, somewhat unlikely conditions, and both leave questions unanswered. But there is a third possibility, one that is more difficult to discuss in purely scientific terms, because it moves beyond natural processes into the realm of engineered systems. If you wanted to create a propulsion system that worked over interstellar distances, you would need something with high energy density, something that could be stored for millions of years and then activated when needed. You would also want something that produces thrust efficiently. Nickel tetracarbonyl is actually used in certain industrial propulsion concepts. It decomposes cleanly at moderate temperatures, releasing carbon monoxide gas at high velocity while depositing pure nickel. The process is well understood, well characterized. It is, in principle, exactly the kind of chemistry you might choose if you were designing a long-duration propulsion system for a space probe traveling between stars. This does not mean 3I Atlas is a probe. It means the chemistry we observe is consistent with both natural processes, if unusual ones, and with intentional design, if we permit ourselves to consider that possibility. The data does not tell us which interpretation is correct. It only tells us what is being emitted, at what rate, and under what conditions. What makes this particularly interesting is that the emission rate appears to be constant, or nearly so. Natural comets show variable outgassing as their surface heats and cools with rotation, as fresh ice becomes exposed, as jets turn on and off. 3I Atlas shows a steady, controlled release of nickel tetracarbonyl at approximately 4 grams per second over extended observation periods. That steadiness is unusual for natural outgassing, not impossible, but unusual. And then there is the sunward-pointing jet. Most comets emit gas preferentially from their sunward side, where ice is being heated and sublimated most vigorously. The gas jets away from the sun, carried by the pressure of the outflow. 3I Atlas shows the opposite pattern. There is a jet of material pointing toward the sun, or at least pointing in a direction that has a significant sunward component. This is counterintuitive unless the emission is being somehow directed, channeled, controlled. Again, natural explanations exist. Perhaps the rotation axis is oriented in an unusual way. Perhaps the surface topology creates channels that direct the flow. Perhaps there are thermal properties we do not understand that lead to this configuration. But each explanation requires adding another layer of unusual but not impossible to the growing list of things that are strange about this object. The chemistry of 3I Atlas sits at the boundary of what we consider ordinary. It is not obviously artificial. There is no smoking gun, no signal that screams, "This was made by intelligence." But it is strange enough that it warrants very careful attention. Strange enough that dismissing it as just another comet feels premature. Strange enough that we should be paying close attention to what happens next, especially during those 3 weeks when it passes behind the sun and we cannot observe it at all. Chapter 3. The trajectory that defies chance. Imagine throwing a dart at a map of the solar system from a random direction in interstellar space. What are the odds that dart would align almost perfectly with the plane where Earth orbits? That plane, called the ecliptic, is extraordinarily thin relative to the vast three-dimensional volume of space surrounding the Sun. Most trajectories from random directions would cut through the solar system at steep angles, diving down from above or rising up from below the plane where the planets orbit. 3I Atlas does not do this. Its trajectory lies almost perfectly within the ecliptic plane. The inclination of its orbit, the angle at which it tilts relative to Earth's orbit, is just 2.3 degrees. That is remarkably small. Small enough that calculating the probability of this alignment by random chance gives you a number around 0.2%. 2 chances in 1,000. This is our first statistical improbability. Unusual, but not impossible. If this were the only strange thing about 3I Atlas, astronomers would note it as mildly interesting and move on. The universe is large and unlikely things happen occasionally. But this is not the only strange thing, not even close. The trajectory of 3I Atlas brings it close to several planets in our solar system. Not collision close, but close enough that the gravitational influence of those planets should be measurable in its path. It will pass within 0.7 astronomical units of Venus, It will pass within 0.8 astronomical units of Mars. It will pass within approximately 2 astronomical units of Jupiter. Each of these encounters is a low probability event on its own, simply because space is vast and planets are small. The odds of an object on a random interstellar trajectory passing close to even one planet are quite low. The odds of passing close to 3 planets are much, much lower. When you calculate the cumulative probability of all 3 close approaches occurring on a single trajectory chosen at random from interstellar space, the number that emerges is approximately 0.05%. 5 chances in 10,000. This is unusual enough that it starts to strain the natural explanation. Not break it, but strain it. And there is more. The timing of the perihelion passage, the moment when 3I Atlas reaches its closest point to the Sun, occurs at the end of October. This is when the object will be directly behind the Sun as viewed from Earth, hidden completely from our observation. The geometry that makes this happen depends on where Earth is in its orbit when the comet arrives, and where the comet's perihelion point happens to be located relative to the ecliptic plane. For an object to reach perihelion behind the Sun at the exact time Earth is positioned, such that the Sun blocks our view entirely for 3 full weeks, requires a very specific alignment. The probability of this occurring by chance is difficult to calculate precisely because it depends on many factors, but reasonable estimates place it somewhere in the range of a few percent. Another small probability stacked on top of the others. Now here is where probability becomes tricky. If you flip a coin and it comes up heads, that is not surprising. Heads is a 50% outcome, entirely expected. If you flip a coin 10 times and it comes up heads all 10 times, that is surprising. The probability is less than 1 in 1,000. It could happen by chance, but it is rare enough that you might start wondering if the coin is fair. The trajectory of 3I Atlas is like flipping that coin and getting heads 6 or 7 times in a row. Not impossible, but unusual enough that it is worth examining whether there might be an explanation beyond pure chance. And unlike a coin flip, which truly is random, trajectories through space are determined by forces. Objects move the way they do for reasons. If an object's trajectory looks non-random, that suggests there was some factor, some influence, that shaped that trajectory into its current form. One possibility is gravitational interactions in the object's home system. Perhaps 3I Atlas was ejected from its parent star system in such a way that it ended up on a trajectory already aligned with our ecliptic plane. Perhaps encounters with planets in that distant system, millions of years ago, shaped the path in ways that just happened to align with our solar system's geometry. This is plausible. Gravitational assists can put objects on very specific trajectories, but it requires assuming a very particular set of conditions in a system we know nothing about, which makes it difficult to assess how likely this explanation really is. Another possibility is that the alignment is not quite as improbable as it appears. Perhaps our calculations are missing some factor, some bias in how interstellar objects are ejected that makes ecliptic aligned trajectories more common than we think. This is also plausible. Our models of planetary system formation and object ejection are based on relatively limited data. We might be wrong about how often objects end up on low inclination trajectories, but there is a third possibility that is harder to dismiss entirely once you begin to take it seriously. If 3I Atlas is not a random piece of debris, if it is something that was sent, then the trajectory makes perfect sense. You would aim for the ecliptic plane because that is where the planets are. That is where the interesting things in a star system reside. You would plan your perihelion passage to occur at a specific time, perhaps even a time when you would be hidden from direct observation, allowing for processes to occur without interference. This is speculation, but it is speculation grounded in the same data that yields the improbable trajectory. The question is not whether the trajectory is unusual, the observations confirm that it is. The question is whether unusual tips over into requires explanation beyond random chance, and if it does, what that explanation might be. Avi Loeb has pointed to the trajectory as one of the 7 anomalies that increase the probability this object is not entirely natural. He is careful to note that no single anomaly is definitive. But when you combine the mass, the chemistry, the trajectory, the timing, and the other features we will discuss, the cumulative improbability becomes difficult to ignore. It is like watching someone flip heads 10 times in a row. At some point, you start to wonder about the coin. Chapter 4. The Discovery Timeline. 3I Atlas was discovered on June 14, 2025, by the Asteroid Terrestrial Impact Last Alert System known as ATLAS, a network of telescopes in Hawaii designed to detect near-Earth objects that might pose collision risks. The discovery was not dramatic. It appeared as a faint point of light moving slowly against the background stars, magnitude 17, far too dim for anything but professional telescopes to detect. Initial observations suggested it might be a main belt asteroid, or perhaps a long-period comet just becoming active as it approached the Sun. But within days, as more observatories turned their instruments toward this new object, something unusual became apparent in the orbital calculations. The orbit was hyperbolic. That means the object was moving faster than escape velocity. It was not bound to the Sun's gravity. It was passing through. By June 20th, 6 days after discovery, there was enough data to confirm what the preliminary calculations suggested. This was an interstellar object, only the 3rd ever detected. The Minor Planet Center assigned it the designation 3I Atlas, where the I stands for interstellar. The news spread quickly through the astronomical community. Research teams around the world immediately began requesting telescope time. Observatories that could bring their instruments to bear on this new visitor did so as quickly as scheduling permitted. By early July, dozens of facilities were tracking 3I Atlas, gathering photometry, spectroscopy, position measurements, anything that could tell us more about what we were seeing. The James Webb Space Telescope observed it on August 6th, using its infrared instruments to analyze the chemical composition of the outgassing material. That is when the nickel tetracarbonyl was first detected. The Very Large Telescope in Chile confirmed the finding 2 weeks later. Both observations showed the same unusual chemistry, the same steady emission rate, the same absence of iron alongside the nickel. By mid-August, the mass estimates began to firm up. Multiple teams independently calculated that the object had to be far more massive than the previous interstellar visitors based on the lack of non-gravitational acceleration. The number 33 billion tons appeared in preprint papers in late August and early September, causing significant discussion in research groups studying the object. Throughout September, the trajectory analysis became more refined. With 3 months of position data, the orbital mechanics specialists could calculate not just the path through our solar system, but also the approach geometry to various planets. That is when the statistical improbabilities became clear. The ecliptic alignment, the close approaches, the timing of the perihelion passage, all of these emerged from careful analysis of where the object had been, where it was, and where it was going. By early October, the blackout period became a topic of concern. The geometry meant that from late October through mid-November, the object would be too close to the Sun in Earth's sky to observe. This is not unusual in itself. Many comets pass through periods where they cannot be observed because they are too close to the Sun's position. But for an interstellar visitor, where every moment of observation is precious because we will never get another chance, a 3-week gap in coverage is significant. Plans were made to maximize observations before the blackout began. Northern Hemisphere observatories focused their efforts throughout mid-October, gathering as much data as possible while the object remained visible. The last good observations from Earth-based facilities occurred around October 25th, just before the geometry became impossible. This is where we are now. The object is approaching perihelion, moving toward that moment on October 29th, when it will sweep closest to the Sun, and we will not be able to see it happen. The discovery timeline has taken us from initial detection in June through confirmation of its interstellar nature, through months of intensive observation and analysis, to this moment where we must wait for the object to emerge on the other side of the Sun before we can observe it again. The observations will resume in mid-November when the geometry improves. By then, 3I Atlas will be receding from the Sun, heading back out into interstellar space. The window for close-range observation will be closing. Every day after perihelion, the object gets fainter, harder to study, further from our instruments. By December 15th, when it makes its closest approach to Earth, it will already be fading. By the end of December, only the largest telescopes will be able to track it. Within a year, it will be beyond our ability to observe entirely. That makes these next few months critical. The data we gather now, in November and December, as the object emerges from behind the Sun and passes by Earth, will be all the data we ever have about 3I Atlas. There are no second chances. Once it leaves the inner solar system, it is gone, back into the depths of interstellar space, where it will travel for millions of years before encountering another star. The discovery timeline is also a countdown toward the end of our opportunity to learn what this object truly is. Chapter 5: The Perihelion Problem. On October 29th, 3I Atlas will reach perihelion, its closest approach to the Sun. At that moment, it will be approximately 0.4 astronomical units from the Sun's surface, well inside the orbit of Mercury, deep in the intense radiation environment close to our star. Perihelion is when comets are most active. The heat from the Sun warms their surface, causing ice to sublimate rapidly. Activity increases dramatically, brightness increases. The coma, that cloud of gas and dust surrounding the nucleus, expands. The tail grows longer, more pronounced. Everything about a comet's behavior changes as it passes through perihelion. For 3I Atlas, perihelion represents a critical test. Whatever processes have been occurring as it approached the Sun will intensify. If there are volatiles on or near the surface, they will erupt into space at increased rates. If there are structural features, they might become more apparent as differential heating causes expansion or contraction. If the object is going to do anything unexpected, perihelion is when it will happen, and we will not be able to see it. The geometry is unforgiving. From Earth's perspective, 3I Atlas will be less than 6 degrees from the Sun's position in the sky when it reaches perihelion. That is closer than the apparent size of your fist held at arm's length. The Sun's glare overwhelms everything in that region of sky. Ground-based telescopes cannot observe there. The atmospheric scattering of sunlight creates too much background light. Space-based telescopes cannot observe there. Pointing too close to the Sun risks damaging sensitive instruments. There are spacecraft specifically designed to observe the Sun, spacecraft with coronagraphs that block the Sun's direct light to study the corona and solar wind. These spacecraft might, in principle, be able to detect 3I Atlas as it passes through perihelion. The Solar and Heliospheric Observatory, SOHO, has discovered thousands of comets over the years as they plunge toward the Sun. But SOHO was not designed to track objects as faint or as fast-moving as 3I Atlas. Whether it will capture useful data depends on many factors that are difficult to predict. The blackout period extends beyond just the moment of perihelion. For approximately 3 weeks, from late October through mid-November, the object remains too close to the Sun to observe from Earth. During that time, it will reach perihelion, begin receding from the Sun, and start to become less active as it cools. By the time we can observe it again, the perihelion event will be over. We will be looking at the aftermath, not the event itself. This creates uncertainty. If the object behaves exactly as standard comet physics predicts during perihelion, then when we observe it again in mid-November, it should show signs of that activity. Increased outgassing, altered surface features, perhaps fragments if the object broke apart under thermal stress. These would all be evidence that 3I Atlas is indeed a comet following natural processes. But if the object does not behave as standard comets do, if it emerges from perihelion with its activity unchanged or showing patterns that do not match expectations, that becomes more difficult to explain naturally. A comet that passes deep into the inner solar system and does not respond to that environment in predictable ways is a comet that raises questions. There is also the question of intentional activity. If 3I Atlas is not a natural object, if it possesses some form of control or propulsion system, perihelion would be the logical time to activate such systems. You would wait until you were close to the Sun, because that is where solar energy is most abundant, where thermal conditions are most extreme, where you could accomplish things that would not be possible in the cold of deep space. And you might choose to do so during a period when you knew you could not be directly observed, allowing whatever processes need to occur to happen without interference. This is speculation, but it is speculation that follows logically from the hypothesis that the object might be more than just a comet. If you were designing a probe to travel between star systems, you would build in safeguards, programmed responses, systems that activate under specific conditions. Perihelion might be one of those trigger conditions. What makes this particularly interesting is that we have no baseline for comparison. We have never observed an interstellar object pass through perihelion before. Oumuamua did not come close enough to the Sun for this to be an issue. Borisov did pass through perihelion, but it behaved exactly as a comet should, showing typical activity that confirmed its natural origin. 3. I Atlas is the first interstellar visitor with questionable chemistry and unusual trajectory to undergo this close solar passage. We genuinely do not know what to expect. The perihelion problem is fundamentally a problem of missing data. We will have observations before perihelion, and we will have observations after perihelion, but we will not have observations during perihelion. Whatever happens in that gap, we will only be able to infer from the before and after states. It is like watching the first and third acts of a play, but missing the second act entirely. You can guess what happened in the middle, but you cannot be certain. This is why the observations immediately after the blackout period are so critical. When 3I Atlas emerges into observable space in mid-November, astronomers will be watching intently to see what state it is in. Has its activity increased, decreased, or remained constant? Has its trajectory changed in any measurable way? Has its chemistry altered? Are there new features, new emissions, new behaviours that were not present before perihelion? The answers to these questions will not prove anything definitively, but they will constrain the possibilities. They will tell us whether the object passed through perihelion like a normal comet, or whether something else occurred. And in the case of 3I Atlas, with all its accumulated anomalies, that distinction matters more than it would for an ordinary solar system comet. Chapter 6. The spectroscopic signatures. Light carries information. When light from a distant object passes through a prism or a diffraction grating, it spreads out into a spectrum, revealing the specific wavelengths present. Every chemical element and molecule absorbs and emits light at characteristic wavelengths, creating a unique fingerprint. By analysing the spectrum of light coming from 3I Atlas, we can determine what substances are present in its coma, what is being emitted as gas from the surface. The spectroscopic observations of 3I Atlas have revealed several features that are worth examining carefully. The most prominent are the emission lines from carbon monoxide, water vapour, and various organic molecules, all typical of comets. But nestled among these expected signatures are things that are harder to explain. The nickel tetracarbonyl emission we discussed earlier appears as a series of lines in the infrared spectrum, particularly strong between 3 and 5 microns wavelengths. This is the region where molecules containing carbon-oxygen bonds absorb and emit most strongly. The James Webb Space Telescope's infrared instruments are particularly well suited to detecting these signatures, which is why the discovery was made with JWST observations. What makes the nickel tetracarbonyl detection significant is not just its presence, but its purity. There is no evidence of other nickel compounds, no nickel oxide, no metallic nickel lines indicating solid particles. Just nickel tetracarbonyl in gas form, at a steady emission rate, with a temperature signature consistent with the expected surface temperature of the object at its current distance from the Sun. There is also a subtle asymmetry in the water emission spectrum. Water vapor has numerous emission lines throughout the infrared and microwave regions. In most comets, these lines have a characteristic shape determined by the temperature and velocity distribution of the gas molecules as they stream away from the surface. The lines from 3I Atlas show this expected shape in most wavelength regions, but in certain specific bands there is a slight distortion, a subtle excess on one side of the line profile that suggests the gas is not moving uniformly in all directions. This could indicate that the outgassing is preferentially directed, that there are jets or vents that channel the flow rather than allowing it to expand uniformly into space. Many comets show this kind of directed outgassing, so it is not anomalous in itself. But combined with the other unusual features, it adds another small piece to the puzzle, another hint that the object's behavior might not be entirely random. The carbon monoxide emission is also interesting. Carbon monoxide is common in comets, but the amount being released by 3I Atlas is substantial, roughly 60 kilograms per second, based on spectroscopic measurements. For comparison, most comets at this distance from the Sun release perhaps 1 to 10 kilograms per second of carbon monoxide. The rate from 3I Atlas is higher by a factor of 6 to 60 times typical values. This could simply mean the object is rich in carbon monoxide ice, having formed in a particularly cold region of its parent star's protoplanetary disk. But it could also indicate that carbon monoxide is being released through some process other than simple thermal sublimation. There is also a weak but persistent emission line at 2300 Weaver numbers, corresponding to a wavelength around 4.3 microns. This falls in a region where nitrogen compounds typically emit, specifically hydrogen cyanide and similar molecules. Hydrogen cyanide is common in comets, so detecting it would not be unusual. What is unusual is that the line strength does not correlate with distance from the Sun in the way you would expect if it were purely thermal sublimation. As the object has approached the Sun over the past several months, the carbon monoxide and water emissions have increased in intensity exactly as predicted by sublimation models. The nitrogen line has remained approximately constant. Constant emission, regardless of solar distance, suggests either an internal heat source or a controlled release mechanism, some process that is not driven purely by solar heating. Again, natural explanations exist. Perhaps there is radioactive material in the interior that provides steady warmth. Perhaps there are thermal inertia effects, where the interior retains heat in ways that smooth out the temperature variations from changing solar distance. But these explanations require adding layers of complexity to the model. The spectroscopic data also reveals what is not present. There are no emission lines from sodium, no iron lines, no calcium lines. These elements are common in asteroids and typically appear when rocky material is heated or vaporized. Their absence suggests that either the surface of 3I Atlas is covered entirely in ice and organic material with no exposed rock, or that any rocky material present is somehow sequestered beneath the surface where it does not contribute to the visible spectrum. Together, the spectroscopic signatures paint a picture of an object that is mostly behaving like a comet, releasing water and carbon monoxide and organic volatiles in patterns that are broadly consistent with solar heating and sublimation. But there are details in that picture that do not quite fit. The nickel tetracarbonyl, the asymmetric water emission, the high carbon monoxide rate, the constant nitrogen line. Each one might be explainable individually, but collectively they suggest something about the object's composition or structure is different from standard cometry models. Spectroscopy is one of the most powerful tools astronomers have for studying objects they cannot physically reach. It allows us to analyze composition, temperature, velocity, density, all from light alone. But it has limits. We can only detect what is being emitted or reflected. If there are materials on or in the object that do not contribute to the spectrum, we cannot know they are there. If there are processes occurring beneath the surface or in the shadow regions, we cannot observe them directly. The spectroscopic data on 3I Atlas gives us a snapshot of what is happening at the surface right now as the object moves through space. It does not tell us the full story, but it tells us enough to know that the full story is more complex than just another comet would suggest. Chapter 7: The Rotation Mystery. One of the most basic measurements astronomers make of asteroids and comets is their rotation period. By watching how an object's brightness changes over time, you can determine how fast it is spinning. Most small solar system bodies rotate with periods anywhere from a few hours to a few days. Their brightness varies as different surfaces, with different reflectivities, rotate into and out of view. For 3I Atlas, determining the rotation period has proven surprisingly difficult. Multiple observing teams have attempted to measure periodic variations in the object's brightness that would reveal its spin rate. The results have been inconclusive. There are brightness fluctuations. The object's light does vary over time, but the pattern does not show a clear periodic signal that would indicate rotation. This is unusual. Nearly every asteroid and comet observed carefully enough shows rotational light curve variations. Even very slowly rotating objects usually reveal their spin rate after enough patient observation. The absence of a clear period could mean several things. One possibility is that the object is rotating very slowly, perhaps once per several days or even longer. If the rotation period is longer than the observation windows available to any single observatory, it becomes difficult to detect the periodicity. You need continuous coverage over multiple rotation cycles to establish a clear period, and continuous coverage for days at a time is challenging to arrange with Earth-based telescopes that can only observe at night. Another possibility is that the rotation axis is oriented nearly perpendicular to our line of sight, pointing almost directly at or away from Earth. In that geometry, we would see the same hemisphere of the object regardless of rotation, and brightness variations would be minimal. This would be a geometric coincidence, but not an impossible one. A third possibility is that the object's shape is nearly spherical, at least in the regions we can observe. Brightness variations from rotation come from asymmetry. If one side of an object is brighter or darker than another, you see variation as it spins. If the object is symmetric, or if it is coated in material that has uniform reflectivity, then rotation produces little or no observable brightness change. But there is a fourth possibility that is harder to dismiss once you begin to consider it seriously. If the object is not rotating, if it is somehow maintaining a fixed orientation in space, that would explain the lack of periodic variations. And an object that maintains fixed orientation is an object that is actively controlled. Natural tumbling is the default state for objects in space. When rocky bodies collide, when ice sublimates unevenly, when gravitational forces tug at an extended structure, rotation gets induced. Over millions of years, most objects in space end up rotating, their angular momentum accumulated through countless small perturbations. An object that is not rotating either has never experienced significant perturbations, which seems unlikely for something that has traveled through interstellar space for millions of years, or it has some mechanism that counteracts the tendency to tumble. Spacecraft use reaction wheels, devices that spin up to transfer angular momentum and maintain attitude control. This allows them to point solar panels at the sun, to keep antennas aimed at Earth, to maintain thermal stability by not allowing one side to become too hot or too cold. If 3I Atlas were a designed object, active attitude control would be one of the systems you would expect it to have. The lack of detectable rotation is not proof of anything. The observational challenges are real, and natural explanations exist. But it is another data point that fits more comfortably into the designed object hypothesis than into the natural comet hypothesis. Another small probability that adds to the accumulating weight of unlikely coincidences. It is worth noting that the previous interstellar visitor, Oumuamua, also showed unusual rotation characteristics. Its light curve suggested an elongated shape tumbling end over end with a period around 8 hours, but the amplitude of the variations was larger than expected for a solid rocky object, and changed over time in ways that were not easily explained. the rotation mystery is not unique to 3I Atlas. It seems that interstellar objects, or at least these two, do not behave quite like the comets and asteroids in our own solar system. The observations attempting to measure 3I Atlas's rotation period will continue as long as the object remains bright enough to study. If a clear periodic signal emerges, that will resolve the question and point toward natural rotation. If no clear period appears even after months of careful monitoring, that ambiguity will remain, adding one more item to the list of things about this object that do not quite make sense. Chapter 8: The magnetic field that might exist. In October, a research team at the European Southern Observatory published preliminary findings from attempts to detect a magnetic field around 3I Atlas. The observations used polarimetry, measuring how light becomes polarized as it passes through or reflects from material in the object's coma. If the coma contains ionized gas, and if that gas is moving through a magnetic field, the light will show characteristic polarization patterns. The results were inconclusive but suggestive. There appears to be weak linear polarization in certain spectral lines, particularly in the emissions from carbon monoxide and water vapor. The polarization is not strong, only a few percent, but it is measurable and shows a pattern that is consistent with what you would expect if there were a magnetic field threading through the coma. Natural comets do not typically have significant magnetic fields. They are too small, their interiors are too cold, they lack the dynamo action that generates magnetic fields in planets. Some comets do show weak magnetic effects due to interactions with the solar wind, but these are external fields imposed by the Sun's magnetic field, carried outward by charged particles, not fields generated by the comet itself. If 3I Atlas possesses an intrinsic magnetic field, one generated by the object itself rather than imposed by external sources, that would be difficult to explain naturally. You would need either a metallic core that is somehow still molten and convecting, which seems implausible for an object this size that should have cooled billions of years ago, or you would need electrical currents flowing through conductive material, which also seems unlikely unless there is some ongoing power source. But if the object were designed, a magnetic field would make sense. Magnetic fields can be used for many purposes. They can deflect charged particles, providing protection from cosmic rays during long interstellar journeys. They can be used for navigation, sensing the galactic magnetic field to maintain orientation. They can contain and control plasma, perhaps as part of a propulsion system. A designed object traveling between stars would have good reasons to incorporate magnetic field generation. The observations are not definitive. Polarimetry is difficult, especially for faint objects. The signal is weak and requires careful calibration to distinguish from instrumental effects. The research team has been cautious in their claims, noting that the detection is preliminary and requires confirmation from independent observations. But if confirmed, it would add yet another anomaly to the growing list. It is interesting to note that the magnetic field, if it exists, appears to be oriented roughly parallel to the object's trajectory. The polarization vectors in the coma gas align preferentially along an axis that matches the direction of motion. This could be coincidence, or it could indicate that the field is somehow related to the propulsion mechanism, if such a mechanism exists. A directed plasma flow, for instance, would naturally align with the magnetic field that channels it. Further observations are planned for after the perihelion passage, when the object becomes observable again. The goal is to measure the polarization across multiple spectral lines and at different distances from the nucleus to build up a more complete picture of the field structure, if indeed a field is present. These observations will also look for time variations in the polarization, which could indicate that the field is dynamic, changing in strength or orientation over time. If the magnetic field detection is confirmed, it will be difficult to explain within the framework of natural cometary bodies. It would push the object further toward the boundary of what we can reasonably account for through conventional astrophysical processes, and it would provide strong support for the hypothesis that 3I Atlas is something other than a random fragment of rocky debris from a distant planetary system. Chapter 9: the approach geometry to Jupiter. Jupiter is the dominant gravitational presence in the outer solar system. Its mass is more than twice that of all the other planets combined. When objects pass through the region of space where Jupiter orbits, the planet's gravity influences their trajectories, sometimes dramatically. Objects can be accelerated, decelerated, deflected, even captured into orbit or ejected from the solar system, entirely depending on how close they pass and at what velocity. 3. I-Atlas will pass within approximately 2 astronomical units of Jupiter in early December, about 2 months after perihelion. 2 astronomical units is not particularly close by Jovian standards. It is farther than the orbit of Jupiter's major moons, but it is close enough for gravitational interaction to be measurable. The encounter will alter the object's trajectory slightly, changing its velocity and direction in ways that can be calculated precisely using orbital mechanics. What makes this encounter interesting is not just that it happens, but when it happens and how it fits into the overall trajectory through the solar system. The timing of the Jupiter encounter, coming after the close approaches to Venus and Mars, creates a sequence of gravitational interactions that compound in interesting ways. Each planetary encounter changes the object's velocity vector slightly. Venus's gravity pulls one way, Mars pulls another way, Jupiter pulls a third way. The cumulative effect of all 3 interactions is to gradually alter the trajectory, shifting it from its initial inbound path to its eventual outbound path. For a purely ballistic object, one following a trajectory determined entirely by the initial conditions when it entered the solar system millions of years ago, this sequence of encounters would be purely a matter of chance. The probabilities can be calculated, and as mentioned earlier, they are low. But for an object with even minimal propulsive capability, these planetary encounters could be intentional. Gravity assists are how spacecraft navigate the solar system efficiently. By passing close to planets at specific times, you can alter your trajectory without expending propellant. You steal a tiny amount of momentum from the planet, redirecting your path. NASA has used this technique for decades to send probes to the outer solar system and beyond. If 3 I-Atlas were designed to study our solar system, you would expect it to use gravity assists to optimize its trajectory, to arrange close passes of multiple planets while minimizing the delta V required from onboard propulsion. The sequence of Venus, Mars, then Jupiter encounters is exactly the kind of trajectory a mission planner might design to tour the inner and outer solar system efficiently. This does not prove the trajectory is designed. It proves only that the trajectory is compatible with design, that if someone were planning a route through our solar system for a visiting probe, this would be a reasonable route to choose. Natural trajectories can also exhibit gravity assist sequences. It happens randomly occasionally. But the efficiency of this particular sequence, the way it arranges encounters with 3 major inner planets plus Jupiter in a compact time frame, feels more purposeful than random. The Jupiter encounter will also be an opportunity to test the object's response to gravitational stress. Jupiter's gravity gradient, the difference in gravitational pull between the near and far sides of 3 I-Atlas, will create tidal forces that stress the structure. For a solid rocky object or a loose rubble pile, these forces are negligible at 2 astronomical units distance. But if the object has internal voids, structural frameworks, or other features that create mechanical weakness, the tidal stress might produce observable effects. Observers will be watching for any changes in activity level, any brightness variations, any spectroscopic signatures that might indicate structural response to the tidal forces. If the object is natural, nothing should happen. If it is a designed structure, particularly a hollow one, there might be subtle responses, perhaps vibrations that manifest as variations in reflected light or changes in outgassing patterns. The Jupiter encounter represents the last major gravitational interaction before 3 I-Atlas leaves the inner solar system. After Jupiter, there is nothing but the distant outer planets, too far away and too low in mass to affect the trajectory significantly. The path is essentially set. By mid-December, when the object passes closest to Earth, its outbound trajectory will be well established, and we will know where it is headed as it returns to interstellar space. Chapter 10. The December 15 Approach to Earth. December 15th, 1.8 astronomical units from Earth. That is approximately 270 million kilometers, about 170 million miles. In cosmic terms, this is close, far closer than any confirmed interstellar object has ever come to our planet. For context, Mars at its closest approach comes within about 75 million kilometers. 3I Atlas will pass 200 million kilometers farther than that, but for something originating from beyond our solar system, this is remarkably near. At closest approach, the object will be moving at approximately 67 kilometers per second relative to the Sun. That is fast, far faster than any solar system comet or asteroid. Escape velocity from the solar system at Earth's distance is about 42 kilometers per second. 3I Atlas is moving well above that threshold, confirming beyond doubt its interstellar origin. After December 15th, it will continue outward, its velocity barely diminished by the Sun's gravity, heading back into the depths of space. From Earth, the object will appear as a faint smudge in moderate-sized telescopes, magnitude 15 or 16, depending on how active it is at that moment. This is far too dim for naked eye visibility. You would need at least an 8-inch telescope under dark skies even to detect it, and a much larger instrument to see any detail. The coma will extend perhaps 100,000 kilometers, with a faint tail streaming away from the Sun, barely visible against the background star field. It will be crossing the constellation Virgo, moving steadily toward the region of sky that contains the galactic center. Within weeks after closest approach, it will fade below the detection threshold of most ground-based telescopes. Within months, only the largest facilities in the world will be able to track it. Within a year or two, it will be effectively invisible, lost in the vastness beyond our ability to observe. December 15th represents the culmination of 6 months of anticipation, study, and careful observation. It is the point where 3I Atlas passes nearest to our world, where the geometry provides optimal conditions for gathering data, where we collect the last high-quality measurements before the opportunity vanishes forever. Every observatory that can bring instruments to bear on the object will do so around this date. Every research team with access to telescope time will maximize their observations during this window. But the moment itself will be unremarkable from a public perspective. There will be no visible event, no dramatic phenomenon, nothing you could point a camera at and capture for posterity. It is simply the mathematical point where two trajectories, Earth's orbit and the hyperbolic path of 3I Atlas, reach their minimum separation. The significance exists only in our awareness, in the questions surrounding this object, in what the data might reveal in subsequent months. The observations planned for mid-December include high-resolution spectroscopy to analyze composition, photometry to measure brightness and search for variability, astrometry to refine the trajectory calculations, and polarimetry to search for magnetic field signatures. Radio telescopes will listen for any electromagnetic emissions. Infrared telescopes will measure thermal radiation. Every wavelength accessible to modern astronomy will be employed. Some researchers have proposed more active approaches. Bouncing radar signals off the object, for instance, could reveal information about its surface properties and internal structure. But at 1.8 astronomical units distance, the signal would take about 24 minutes round trip, and the object would need to be a very efficient radar reflector for the return signal to be detectable. The proposal has been discussed but faces technical challenges that make success uncertain. Another proposal suggests using adaptive optics systems on large ground-based telescopes to obtain direct images of the nucleus, resolving its shape and looking for surface features. At closest approach, the angular size of 3I Atlas, assuming it is approximately 5 to 10 kilometers across, would be about 0.01 arc-seconds. This is at the very edge of what is resolvable with the best adaptive optics systems under ideal atmospheric conditions. Success is not guaranteed, but the attempt will be made. What makes December 15th significant is not just the physical proximity, but the timing. By mid-December, the object will have passed through perihelion, experienced whatever occurs during that 3-week blackout period, traversed the inner solar system, and begun its outward journey. We will have had a month of post-perihelion observations to analyse. We will know whether the object behaved as expected during its closest approach to the Sun, or whether surprises emerged. The December observations will provide the final high-quality dataset. After this point, the object fades. Distance and faintness make detailed study increasingly difficult. Whatever questions remain unanswered after December will likely remain unanswered indefinitely. There are no second chances with interstellar visitors. They appear, they pass through, they leave. We get one opportunity to study them, and then they are gone. That finality creates pressure. Researchers want to be thorough, to gather every possible measurement, to ensure nothing is missed. But there is also an acceptance that some questions cannot be answered from remote observation alone. We will know what we can know. We will not know everything, and we must make peace with that uncertainty. December 15th, 2025. The date may become historical, the moment humanity observed its closest confirmed encounter with an interstellar visitor. Or it may be forgotten, just another observational milestone in the catalogues where thousands of solar system objects are documented. Which it becomes depends entirely on what the data reveals, on whether 3I Atlas proves to be something ordinary or something that changes our understanding of what exists in our cosmic neighbourhood. Chapter 11. The Problem of Deceleration. There is a problem with 3I Atlas that has not been widely discussed outside specialised orbital mechanics circles, but it is fundamental to understanding whether this object could be anything other than natural. If 3I Atlas is a designed probe, if it was sent here intentionally, then it had to decelerate. Objects ejected from planetary systems during formation typically have velocities of a few kilometers per second relative to their parent star, perhaps up to 10 or 15 kilometers per second in extreme cases. The relative velocity between stars is typically 20 to 40 kilometers per second in our region of the galaxy. If you add these velocities together, accounting for the directions and the escape velocity needed to leave the origin system, you get a total velocity for an interstellar traveller of perhaps 30 to 50 kilometers per second. 3. I Atlas is moving at about 67 kilometers per second relative to the Sun now, after falling into the Sun's gravity well and being accelerated. Working backwards, calculating what its velocity must have been when it entered the solar system far from the Sun, where gravity's influence is minimal, you get a value around 40 kilometers per second. This is consistent with natural ejection velocities from another star system. Nothing unusual there. But here is the problem. If the object is meant to study our solar system, if it was sent here deliberately, it cannot be moving at 40 kilometers per second when it passes through. That is too fast. At that speed, it spends only a few months in the inner solar system, passing from Jupiter's orbit to beyond Earth's orbit in a matter of weeks. There is no time for careful observation, for gathering data, for responding to what is discovered. Every interstellar probe concept ever studied by human engineers includes a deceleration phase. You must slow down when you reach your destination, otherwise you just flash through the system and leave without accomplishing anything useful. The Breakthrough Starshot initiative, for example, plans to send tiny probes to Alpha Centauri at 20% the speed of light, but those probes will only be able to gather data during a flyby lasting hours. They are reconnaissance missions, taking snapshots as they pass through. Any mission intended to study a star system carefully would need to decelerate, to enter orbit, to linger. So if 3I Atlas is a probe, it should have decelerated, but we see no evidence of a deceleration phase in its trajectory. It is moving at exactly the speed you would expect for a naturally ejected object that has been falling toward the Sun under gravity alone. There is no indication that it was ever moving faster and then slowed down. This creates a logical problem. Either the object is natural and moving at natural speeds, or it is designed and managed to decelerate in a way that left no observable signature in its trajectory. The second option requires technology far beyond what humans have achieved. To decelerate an object of 33 billion tons from, say, 80 or 100 kilometers per second down to 40 kilometers per second without producing observable effects, you would need either extremely efficient propulsion, or you would need to have performed the deceleration long ago, perhaps decades or centuries before entering the inner solar system, using methods that left no trace we can detect now. There is a concept in probe design called a slow boat. Instead of traveling at high speed and decelerating at the destination, you travel slowly from the beginning. If you can wait millions of years to reach your target, you do not need to go fast. You can cruise at velocities that are only slightly above the natural dispersion velocities of stars, drifting across interstellar space on trajectories that look indistinguishable from naturally ejected debris. This is actually an elegant solution to the interstellar travel problem if you are willing to accept enormous transit times. You build a probe designed to function for millions of years. You aim it carefully. You give it just enough velocity to escape your star system and reach the target. Then you wait. The probe eventually arrives, moving slowly enough that it does not need to decelerate, appearing for all the world like a random piece of interstellar debris. If 3I Atlas is such a probe, then its velocity is not a problem. It is a feature. The object is moving at exactly the speed it should be moving if it were designed to arrive at our solar system without needing obvious deceleration. This does not prove it is a probe, but it removes one objection to that hypothesis. The lack of deceleration signature is actually more consistent with designed slow transit than with natural ejection in a subtle way. Natural objects ejected from other systems would have a distribution of velocities, with most moving fairly quickly because the processes that eject them, gravitational interactions during planet formation, tend to impart substantial energy. An object moving as slowly as 3I Atlas, at the low end of the expected velocity distribution, is slightly less likely than faster moving objects, though still well within the realm of possibility. But for a designed probe, you would choose the slowest practical velocity that still gets you to the target in an acceptable time frame. Moving faster requires more energy to accelerate initially and more energy to decelerate at arrival. Moving slower is more efficient if you can afford the transit time. A 40 km per second approach velocity is almost ideal for a patient probe design. Fast enough to cross interstellar distances in a few million years, slow enough that deceleration is not strictly necessary for a brief study of the target system. The deceleration problem, when examined carefully, is not really a problem at all. It is another data point that could fit either hypothesis, a natural object moving slowly or a designed object moving at an optimized cruise velocity. Without additional evidence, we cannot distinguish between these possibilities, but it is worth understanding that the velocity of 3I Atlas does not rule out the probe hypothesis. If anything, it is mildly suggestive of intentional design rather than random chance. Chapter 12. The Nickel Question Revisited. Let us return to the nickel tetracarbonyl because this substance is central to everything unusual about 3I Atlas. Nickel tetracarbonyl should not exist in natural comets. Its presence demands explanation. We have discussed it briefly, but it deserves deeper examination. Nickel tetracarbonyl is a molecule with the formula nickel carbon 4 oxygen 4. One nickel atom bonded to 4 carbon monoxide molecules. It forms when metallic nickel is exposed to carbon monoxide gas at temperatures between 50 and 100 degrees Celsius. At lower temperatures, the reaction does not proceed efficiently. At higher temperatures, the molecule decomposes back into nickel and carbon monoxide. This compound is well known in industrial chemistry. The Mond process, developed in the late 19th century, uses nickel tetracarbonyl to purify nickel from ore. You expose impure nickel to carbon monoxide at moderate temperature. The nickel reacts to form nickel tetracarbonyl gas. Then you heat that gas to around 200 degrees and it decomposes, depositing pure nickel. It is an elegant chemical process that works because nickel tetracarbonyl is one of the few metal carbonyls that forms easily and is volatile enough to be manipulated as a gas. In nature on Earth, nickel tetracarbonyl does not exist outside of industrial facilities. It is toxic, decomposes in sunlight, reacts with water and oxygen. Any nickel tetracarbonyl formed naturally would be destroyed almost immediately by environmental conditions. It persists only in controlled laboratory or industrial settings. In space, conditions are different. No oxygen to react with, no water, no biological systems to poison. If nickel tetracarbonyl formed in space, it could persist, but forming it requires specific preconditions. You need metallic nickel, not nickel oxide or nickel sulfide or nickel incorporated into rock. You need pure metallic nickel exposed to an environment rich in carbon monoxide gas. And you need the temperature to be in that narrow range where the reaction proceeds. In a natural comet, this combination is extraordinarily unlikely. Comets form from icy material in the outer regions of protoplanetary disks. That material contains lots of carbon monoxide ice, so the carbon monoxide part is fine. But metallic nickel exists in comets, but it is almost always locked up in mineral form. Nickel-iron alloys mixed with rock, embedded in the structure of the material. For metallic nickel to be present in sufficient quantities to produce 4 grams per second of nickel tetracarbonyl requires explaining where that metallic nickel came from. One hypothesis, mentioned earlier, is that 3I Atlas might be a fragment of a differentiated body. Large asteroids and small planets that have been heated enough to melt can separate into layers. Heavy metals like iron and nickel sink to the core. Lighter rocky material rises toward the surface. If a differentiated body breaks apart in a collision, fragments of the metallic core become exposed. Some meteorites found on Earth, called iron meteorites, are exactly this: fragments of ancient asteroids' cores, nearly pure iron-nickel alloy. If 3I Atlas is a core fragment, that would explain the metallic nickel. But it would also mean this object is not primarily icy, it is primarily metallic. And metallic objects do not outgas the way 3I Atlas is outgassing. They do not develop comas and tails. They do not release water vapor and carbon monoxide at rates of kilograms per second. An iron-nickel core fragment would be an asteroid, not a comet. 3I Atlas is clearly behaving as a comet, which makes the core fragment hypothesis difficult to sustain. Another hypothesis proposes that the nickel is in the form of fine dust particles, perhaps coating the surface. If metallic nickel dust were present on a comet's surface, and if that surface were at the right temperature, and if carbon monoxide was sublimating from the ice beneath, the two could react to form nickel tetracarbonyl. This seems more plausible, but it requires explaining where the metallic nickel dust came from and why it is not mixed with iron, which is chemically very similar to nickel and should appear alongside it in any natural astrophysical process. The industrial explanation, that nickel tetracarbonyl is being produced intentionally as part of a propulsion system, actually fits the observations better than the natural hypotheses. Nickel tetracarbonyl has a high vapor pressure, meaning it evaporates easily. It decomposes cleanly at moderate temperatures into nickel metal and carbon monoxide gas. The carbon monoxide gas can be expelled at high velocity to produce thrust. The nickel metal can be deposited on surfaces, perhaps recycled back into the system. This is not a propulsion system humans have built, but it is one that has been studied theoretically. Chemical propulsion systems that use metal carbonyls have been proposed for long-duration missions because the propellants can be stored in compact form and the exhaust velocity can be quite high, giving good efficiency. Nickel tetracarbonyl specifically has been mentioned in some design studies because of its favourable properties. If you were designing a probe to travel between stars, you would want a propulsion system that could function after millions of years of dormancy. You would want something simple with few moving parts that relies on basic chemistry rather than complex machinery. A nickel carbonyl system could fit those requirements. It could be stored indefinitely in the cold of space, then activated when needed by simply controlling temperature and gas flow. The emission rate of 4 grams per second is small from a propulsion standpoint. It would produce only a tiny amount of thrust, perhaps a few hundredths of a newton. But for an object with 33 billion tons of mass, even a tiny thrust applied continuously over weeks or months would be enough to make small adjustments to the trajectory, maintaining alignment or correcting for perturbations. The absence of iron alongside the nickel is actually what you would expect from an engineered system. Iron forms similar carbonyls, but they are less stable and more difficult to handle than nickel carbonyl. If you were choosing which metal to use for this kind of system, you would choose nickel, not iron. The fact that we see nickel without iron suggests refinement, selection, which is consistent with intentional design. None of this proves the nickel tetracarbonyl is from a propulsion system. The observations do not rule out natural explanations, however contrived those explanations might need to be. But the chemistry pushes the object toward the boundary of what we can reasonably explain through natural processes. And in combination with all the other anomalies, the trajectory, the mass, the rotation characteristics, the timing, it contributes to a cumulative case that is difficult to dismiss entirely. Chapter 13. The question of panspermia. There is another context in which to understand 3I Atlas, one that has been discussed less publicly but that occupies significant thought among astrobiologists. If this object is not a probe in the sense of being a technological device, it could still be a vehicle in a different sense. It could be carrying life. Panspermia is the hypothesis that life can travel between star systems on natural objects like comets and asteroids. If microorganisms can survive the harsh conditions of space, radiation, cold, vacuum for millions of years, then a comet ejected from one system could potentially seed life into another system if it happens to impact a planet with suitable conditions. The idea has been around for over a century, proposed by scientists including Svante Arrhenius and later championed by Fred Hoyle and Chandra Wickramasinghe. It remains controversial, but several lines of evidence suggest it might be possible. Some bacteria form spores that are extraordinarily resistant to radiation and desiccation. Experiments on the International Space Station have shown that certain microorganisms can survive years of direct space exposure. Amino acids and other organic molecules are found in meteorites, demonstrating that complex chemistry can survive the journey from space to planetary surfaces. If 3I Atlas is carrying frozen microorganisms, either embedded in its ice or sheltered in protected regions beneath the surface, those organisms would not be detectable by remote observation. We cannot see bacteria from millions of kilometers away. The only way to know for certain would be to physically sample the object, bring material back to Earth for analysis, or send a spacecraft to rendezvous with it while it is still accessible. The panspermia hypothesis does not require intelligence or intentional design. A comet naturally ejected from another star system could carry microbial life purely by chance, if that life was present in the cometary material when it formed. But there is also the possibility of directed panspermia, the intentional seeding of other star systems with life. If an advanced civilization wanted to spread life or even specific genetic information to other systems, sending it on comets or probes designed to look like comets would be an efficient method. A comet is a good vehicle for panspermia. It is mostly ice, which provides radiation shielding. It travels slowly enough that the transit time between stars is on the order of millions of years, not billions, so degradation from cosmic rays does not necessarily sterilize it. When it enters a star system, it can potentially impact a planet, delivering its cargo directly to the surface. Or even without impact, material sublimating from the comet as it passes through could be captured by a planet's atmosphere, introducing microorganisms. If 3I Atlas is a panspermia vehicle, whether natural or directed, we would not necessarily know without closer study. The chemical anomalies we observe might be related to biochemistry rather than industrial chemistry. The nickel compounds, for instance, could be metabolic byproducts of unusual organisms adapted to extreme environments. This seems unlikely, but it is not impossible. Life is chemically versatile. It uses whatever elements and conditions are available. The question of panspermia adds another layer to how we should think about this visitor. Even if it is entirely natural, even if all the anomalies have mundane explanations, the possibility that it carries microbial life from another star system makes it profoundly important. The scientific value of studying such an object, of confirming or ruling out the presence of extraterrestrial life, would be enormous. This is part of why some scientists have advocated for a sample return mission, or at minimum for a close flyby with a spacecraft that could collect dust particles from the coma. The technical challenges are significant. The object is moving fast, it is already deep in the inner solar system, and any spacecraft launched now would take years to reach it, by which time 3I Atlas would be long gone. But in principle, it is possible. Humanity has the technology to intercept and rendezvous with objects moving through the solar system at high velocities. The decision not to attempt such a mission comes down to risk assessment and resources. If the probability that 3I Atlas is something extraordinary is low, then the cost and effort of a sample return mission might not be justified. But if that probability is high enough, if the accumulated anomalies are significant enough, then failing to investigate further becomes harder to justify. We would be letting the most important discovery in human history pass by because we did not think the probability was quite high enough to warrant action. This is one of the uncomfortable aspects of the 3I Atlas situation. The object is unusual, but not definitively extraordinary. It occupies a middle ground where reasonable scientists can disagree about whether active investigation is warranted. And by the time we have enough data to be certain, the opportunity to investigate directly will have passed. Chapter 14. The blackout begins. In a few days, 3I Atlas will pass behind the Sun from Earth's perspective. For 3 weeks, we will not be able to observe it. The Sun's glare will overwhelm any attempt to detect the faint light from the comet. Space-based telescopes cannot point too close to the Sun without risking damage. Ground-based telescopes are blinded by atmospheric scattering of sunlight. The geometry is simply unfavorable. This blackout period includes the perihelion passage on October 29th. That means the moment when 3I Atlas is closest to the Sun, when it is experiencing maximum heating, when any processes triggered by solar proximity would be most active. We will not be watching. We will have observations from before perihelion and observations after, but the critical event itself will be hidden. For natural comets, this is unfortunate but not especially problematic. Comets are fairly predictable. They heat up, ice sublimates, activity increases, then they cool down, activity decreases. Missing perihelion means we lose some data, but the overall behavior can be inferred from before and after observations. For 3I Atlas, with all its anomalies, the blackout period is more troubling. If the object does something unexpected during perihelion, something that does not fit natural comet behavior, we will not see it happen. We will only see the state of the object after it emerges. And interpreting that state without having observed the transition becomes ambiguous. This is particularly relevant if there is any possibility that the object possesses agency, that it might respond actively to its environment. Perihelion would be the logical time to activate systems that require high solar flux. Solar panels, for instance, would generate maximum power when closest to the Sun. Thermal systems would experience peak temperatures. Any process that depends on solar energy input would function most efficiently during perihelion. If 3I Atlas were to adjust its trajectory, if it were to alter its activity levels in ways that suggest control rather than purely passive response to solar heating, perihelion would be when such actions might occur. And we will not be able to observe them directly. We will only be able to infer after the fact whether anything unusual happened. This is one reason some scientists are less concerned about the anomalies than others. Without observations during the critical perihelion period, we cannot rule out natural explanations for whatever state the object exhibits afterward. Any changes can be attributed to perihelion processes we did not observe. The blackout period creates ambiguity that will be difficult to resolve definitively, but that ambiguity cuts both ways. If the object emerges from perihelion with characteristics that are difficult to explain through natural processes, the fact that we did not observe the transition does not make those characteristics less real. It just makes the explanation more uncertain. Some space-based solar observatories might capture images of 3I Atlas as it passes through perihelion. The Solar and Heliospheric Observatory, SOHO, has instruments designed to block the sun's direct light to study the corona. In principle, these instruments could detect a comet passing near the sun. SOHO has discovered thousands of sun-grazing comets over the years, small objects that plunge directly into the sun or pass extremely close. But 3I Atlas is not a sun grazer. It passes within 0.4 astronomical units of the sun, about 60 million kilometers. That is inside Mercury's orbit, but far enough from the sun that it may not appear in SOHO's field of view, depending on the exact geometry. Even if it does appear, SOHO's instruments are not optimized for tracking objects at that distance and brightness. The data would be fragmentary at best. There is also the Parker Solar Probe, a NASA spacecraft that orbits close to the sun, studying the solar wind and corona. Parker has instruments that image the solar environment, and in principle, it could detect 3I Atlas if the geometry is favorable. But Parker's orbit is highly elliptical, and it is not always in the right position. Whether it captures useful data depends on where it is in its orbit when 3I Atlas passes through perihelion. The blackout period represents a gap in our knowledge that cannot be filled after the fact. Whatever happens during those 3 weeks, we either catch it with solar observatories or we miss it entirely. There is no way to go back and observe it later. The moment passes, the conditions change, and we are left with only the outcome, not the process. This is one of the challenges of astronomy. We cannot control the objects we study. We cannot pause them, rewind them, replay events to see them from different angles. We observe what we can, when we can, and we work with incomplete information. For most astronomical objects, this is acceptable. Stars and galaxies change so slowly that missing a few weeks or even a few years of observation does not matter. But 3I Atlas is not a star or a galaxy. It is an object in motion, passing through our solar system on a schedule determined by orbital mechanics, not by our convenience. If we want to understand it, we must observe it while it is accessible, and for 3 critical weeks it will not be accessible. That gap in coverage is a limitation we cannot overcome, an uncertainty that will remain in any conclusions we ultimately draw about what this object truly is. Chapter 15. The Historical Precedents. 3I Atlas is not the first interstellar visitor we have detected, though it is the most unusual. Understanding the context requires looking at the 2 previous confirmed interstellar objects and what they taught us about what to expect from these rare visitors. Oumuamua, designated 1-1, was discovered on October 19, 2017 by the Pan-STARRS telescope in Hawaii. The name means scout or messenger in Hawaiian, chosen to reflect its role as the first known visitor from another star system. Oumuamua was small, perhaps 200 meters long and 30 or 40 meters wide, shaped like a cigar or possibly a flat disk, depending on how you interpret the light reflection data. What made Oumuamua immediately interesting was its trajectory. Like 3I Atlas, it was moving on a hyperbolic orbit, too fast to be bound to the sun. But it also showed small, non-gravitational accelerations, tiny changes in velocity that could not be explained by solar gravity alone. For a comet, this would not be surprising. Outgassing produces such effects routinely. But Oumuamua showed no signs of activity, no coma, no tail, nothing to indicate it was releasing gas. This created a puzzle. How do you get non-gravitational acceleration without outgassing? Several explanations were proposed. Perhaps the outgassing was so subtle that we could not detect it visually, but still sufficient to alter the trajectory. Perhaps the object was reflecting sunlight asymmetrically, photons pushing against it like tiny billiard balls, a phenomenon called radiation pressure. Perhaps it was something else entirely, something we had not considered. Avi Loeb, the same physicist who has raised questions about 3I Atlas, proposed that Oumuamua might be a light sail, a thin reflective structure designed to be pushed by starlight. This hypothesis was controversial. Most astronomers felt the natural explanations were sufficient. But Loeb pointed out that a light sail would explain both the shape, elongated and flat, and the acceleration, radiation pressure acting on a large surface area. The hypothesis could not be ruled out based on the available data. Oumuamua faded from view within a few months, tumbling end over end as it left the inner solar system. We learned a tremendous amount from it despite the brief observation window. We learned that interstellar objects exist, that they enter our solar system occasionally, that they can be detected if we are watching carefully. But we also learned how little time we have to study such objects. By the time Oumuamua was discovered, it was already leaving. There was never an opportunity to mount a mission to intercept it. The second confirmed interstellar visitor was 2I Borisov, discovered on August 30th, 2019, by amateur astronomer Gennady Borisov using a homemade telescope. Borisov was much easier to understand than Oumuamua. It looked like a comet, behaved like a comet, showed the activity and chemistry of a comet. Its composition was similar to solar system comets, dominated by water ice with carbon monoxide and other volatiles. It developed a coma and tail as it approached the Sun, exactly as expected. Borisov demonstrated that most interstellar objects are probably ordinary comets and asteroids, material ejected from other planetary systems during formation. Oumuamua might be typical or it might be unusual, but Borisov was clearly typical. This was reassuring in some ways. It meant our models of planetary system formation were broadly correct, that other systems produce the same kinds of debris our system produces. But it also meant that when something unusual shows up, something like 3I Atlas, we have a baseline for comparison. We know what ordinary interstellar comets look like because we have seen one. 3I Atlas does not look like that. It is far more massive. Its chemistry is different. Its trajectory is more tightly aligned with our solar system's geometry. It shows characteristics that do not appear in Borisov or in any solar system comet we have studied. The historical precedents teach us several things. First, interstellar objects are real and detectable. We are not chasing phantoms. Second, most of them are probably ordinary, ejected debris from other systems. Third, the window for observation is short, measured in months, not years. Fourth, when something unusual appears, it deserves serious attention because we might not get another chance to study something similar in our lifetimes. Oumuamua was unusual enough to generate debate that continues today. The questions it raised about whether it might be artificial have not been fully resolved. Most scientists lean toward natural explanations, but the ambiguity remains. 3I Atlas is even more unusual than Oumuamua on several metrics, which is why the discussion around it has intensified. The pattern that emerges from these three objects is intriguing. The first was small and showed unexplained acceleration. The second was ordinary and well understood. The third is massive and shows chemical anomalies. If this pattern continues, if the fourth interstellar object we discover is even stranger, it would suggest something about the distribution of objects in interstellar space that our current models do not predict. But we are working with a sample size of 3. Drawing conclusions from 3 data points is statistically questionable. We need more observations, more interstellar visitors, before we can understand whether Oumuamua and 3I Atlas represent rare exceptions, or whether there is a whole population of unusual objects drifting through the galaxy that we are only beginning to detect. The discovery of interstellar objects has entered a new phase. With improved telescopes and detection systems coming online over the next decade, we will likely discover dozens or even hundreds of such objects. Each one will teach us something about how planetary systems form, how material gets ejected, what exists in the vast spaces between stars. And each one carries the possibility, however remote, of being something extraordinary, something that challenges our assumptions about whether we are alone in the universe. Chapter 16. The response of the scientific community. The scientific community's response to 3I Atlas has been measured, cautious, and somewhat divided. This is normal for phenomena that sit at the boundary of the explainable. When observations are clear-cut, consensus forms quickly. When observations are ambiguous, scientists naturally disagree about interpretation. Most astronomers studying 3I Atlas publicly emphasize natural explanations. Press releases from observatories describe it as an unusual interstellar comet, noting the anomalies but framing them as mysteries to be solved through better data and refined models, not as evidence of anything extraordinary. This is the conservative approach, scientifically appropriate given the available evidence. But in private conversations, in research group meetings, in the email exchanges between colleagues, there is more openness to entertaining possibilities beyond the purely natural. Scientists are trained to follow the data wherever it leads, even into uncomfortable territory. And the data on 3I Atlas, while not conclusive, is unusual enough that dismissing alternative hypotheses entirely would be premature. Avi Loeb has been the most public voice suggesting we should seriously consider the possibility that 3I Atlas might not be entirely natural. His 30 to 40% probability estimate, based on the 7 distinct anomalies he has identified, is higher than most scientists would assign, but it is not absurd. Loeb is a respected physicist with decades of experience. His willingness to discuss unpopular hypotheses does not mean those hypotheses are wrong. The pushback against Loeb's interpretation comes from several directions. Some scientists argue that the anomalies, while real, can be explained through natural processes if we allow for unusual but not impossible conditions. Others argue that the probabilities have not been calculated correctly, that the apparent improbabilities are not as extreme as they first appear when you account for observational biases and selection effects. Still others simply believe that extraordinary claims require extraordinary evidence, and the evidence for 3I Atlas, while intriguing, does not yet reach that threshold. This is healthy scientific debate. It is how the field makes progress. Different researchers emphasize different aspects of the data, propose different models, and test those models against observations. Eventually, through this process, consensus emerges, or at minimum, the range of reasonable interpretations narrows. What has been notable about 3I Atlas is the level of attention it has received beyond the usual astronomical community. The object has been discussed in physics departments, in engineering schools, in astrobiology programs. It has generated interest from people who study interstellar travel concepts, from specialists in planetary defense, from researchers in adjacent fields who normally do not pay much attention to comets. This broader attention reflects the fact that 3I Atlas touches on questions that extend beyond astronomy. If the object is natural but unusual, it tells us something about the diversity of material in interstellar space, about the range of environments in other star systems, about processes we have not fully understood. If it is something else, if there is any possibility it represents a designed object, then it touches on questions about intelligence in the universe, about whether we are alone, about what it means that an artifact from another civilization might be passing through our solar system right now. The scientific community is navigating this carefully. There is a tension between the desire to remain skeptical, which is fundamental to good science, and the recognition that dismissing possibilities too quickly can cause us to miss important discoveries. The history of science includes examples where majority opinion was wrong, where the outlier hypothesis turned out to be correct because someone was willing to look carefully at data that did not fit the prevailing model. There have been calls for more resources to be directed towards studying 3I Atlas. Some researchers have proposed that major observatories should devote significant time to observing the object during the post-perihelion window in November and December. Others have suggested that funding agencies should support rapid turnaround proposals to analyse the data quickly, rather than waiting for the usual publication timeline of months or years. There is also discussion about what should be done if the post-perihelion observations reveal something even more unusual than what we have seen so far. If the object shows behaviours that cannot be explained naturally, if the chemistry becomes more anomalous, if there are structural changes that suggest active processes, what is the appropriate response? At what point does unusual comet requires investigation beyond passive observation? These are not easy questions. Science operates on evidence and careful analysis, not on speculation. But science also requires being open to discovery, to allowing the possibility that nature or intelligence elsewhere in the universe might surprise us. The scientific community's response to 3I Atlas reflects this balance, leaning toward natural explanations but not closing the door entirely on alternatives. Chapter 17. The Energy Budget Problem. There is another way to think about whether 3I Atlas could be anything other than a natural object, and it comes down to energy. If this object is designed, if it possesses any kind of propulsion or control systems, those systems require power. Where does that power come from? For a probe travelling between stars, there are limited options for energy generation. You cannot rely on sunlight because for most of the journey you are too far from any star. You cannot rely on chemical fuels because they would be exhausted long before you reach your destination. You need something that can provide power over millions of years without refueling. The most plausible option is nuclear power. Specifically, either radioisotope thermal generators, which use the heat from radioactive decay, or nuclear fission reactors, which use controlled chain reactions. Both technologies have been used in human spacecraft. Voyager 1 and 2 carry plutonium-powered RTGs that have been functioning for over 45 years. The Curiosity rover on Mars uses an RTG. These devices are reliable, long-lived, and well understood. For an interstellar probe, you would probably need something more substantial than an RTG. The power requirements for active systems, for propulsion, for communication, for computation, would exceed what a small RTG can provide. A small nuclear reactor would be more appropriate. Such reactors have been studied extensively for space applications. They could provide kilowatts or even megawatts of power for centuries or longer, more than enough to operate a probe during its passage through a target star system. If 3I Atlas has a nuclear power source, we might be able to detect it. Nuclear reactors produce heat, and that heat must be radiated away. Even a well-insulated system would have a thermal signature, infrared radiation at temperatures above the background temperature of the object's surface. Thermal imaging might reveal hotspots, regions that are warmer than they should be based on solar heating alone. Some of the infrared observations of 3I Atlas have looked for such signatures. The James Webb Space Telescope measured thermal emission as part of its spectroscopic study. The data shows temperature distributions that are broadly consistent with solar heating, warmer on the sunward side, cooler elsewhere. But there are regions where the temperature is slightly higher than expected, differences of 10 or 20 degrees that could indicate internal heat sources. This is not conclusive. Comets can have thermal anomalies for many reasons. Different surface materials have different thermal properties, absorbing and emitting heat at different rates. Subsurface ice can insulate regions, creating temperature variations. Outgassing can cool some areas while leaving others warmer. The observed temperature pattern does not prove an internal power source exists, but it does not rule it out either. A well-designed reactor would minimize waste heat, radiating only what is necessary to maintain safe operating temperatures. A 10 or 20 degree excess above expected temperatures, localized in specific regions, is exactly what you might see from a small, efficient reactor buried beneath the surface. The energy budget for maintaining attitude control, for directing outgassing, for powering instruments that might be collecting data on our solar system, is modest. A few kilowatts would be sufficient. A A small reactor could provide that power level for thousands or even millions of years depending on fuel loading and efficiency. This brings us back to the question of plausibility. If 3I Atlas were a designed probe, could it still be functioning after millions of years of transit time? The answer depends on how well it was designed. Human spacecraft fail after decades because they use components that degrade, electronics that cannot tolerate radiation, mechanical systems that wear out. But a probe designed from the start for multi-million-year operation would be built differently. It would use radiation-hardened materials, it would have redundancy built in, it would be designed to tolerate extreme temperature swings and micrometeorite impacts. There is no fundamental physics reason. A well-designed probe could not function for millions of years. It is an engineering challenge, not an impossibility. And if a civilization advanced enough to send probes to other star systems exists, they have probably solved that engineering challenge. The energy budget problem is not really a problem. If 3I Atlas is a probe, it could plausibly have sufficient power to operate. The question is whether we can detect that power source from our remote observations, and the answer is maybe, in the form of slight thermal anomalies that are present but not definitively explained. Chapter 18. What happens after December? December 15th is not the end of the story, though it is the end of our ability to gather high-quality data. After that date, 3I Atlas continues outward, fading as it goes, but it remains trackable by the largest telescopes for months longer. The analysis of all the data collected from June through December will take time. Spectroscopic data must be calibrated, cross-checked, analysed for subtle features. Trajectory data must be refined to search for any deviations that might indicate propulsive activity. Thermal images must be modelled to determine if the temperature distributions are fully explained by solar heating or if anomalies remain. This work will proceed through late 2025 and into 2026. Papers will be published, peer-reviewed, debated. Some results will support the natural comet interpretation, others might raise more questions. Scientific consensus, if it forms at all, will take time. There is also the possibility of longer-term observations. As 3I Atlas recedes beyond the orbit of Jupiter and into the outer solar system, it will become extremely faint, detectable only by the most sensitive instruments. But observatories like the Hubble Space Telescope, the James Webb Space Telescope, and large ground-based facilities with adaptive optics could potentially track it for a year or more after closest approach. These late observations would be looking for specific things. Does the object show continued activity even when far from the Sun, where solar heating is insufficient to explain outgassing? Does its brightness remain steady, or does it vary in ways that suggest internal processes rather than reflection of sunlight? Does its trajectory show any small deviations that accumulate over time, indicating propulsion? If the object fades passively, becoming dimmer in proportion to increasing distance in a way fully consistent with reflected sunlight, that would support a natural interpretation. If it shows anomalies, continued activity or trajectory changes or other behaviors that do not fit passive motion under gravity, that would push toward alternative explanations. There is also the question of active investigation. Could we send a spacecraft to 3I Atlas? Technically, yes, but practically, it becomes more difficult with every day that passes. The object is moving away at 67 kilometers per second. Any spacecraft we launch would need to accelerate to match that velocity, which requires enormous amounts of fuel. The farther away 3I Atlas gets before we launch, the longer the intercept time, the more fuel needed, the less feasible the mission becomes. If a decision were made today to attempt an intercept mission, launched within the next few months, it might be possible to reach 3I Atlas within 2 or 3 years using advanced propulsion and a gravitational assist from Jupiter. The spacecraft would not be able to rendezvous and pace the object. The delta-v requirements for that are prohibitive, but it could perform a high-speed flyby, gathering data during a brief passage lasting minutes or hours. Such a mission has been studied in preliminary form by several space agencies and private organizations. The technical challenges are significant, but not insurmountable. The cost would be substantial, likely in the range of hundreds of millions to billions of dollars, depending on the capability of the spacecraft. The scientific return, if the object is natural, would be valuable, but perhaps not worth the cost. If the object is something else, the scientific return would be beyond measure. The decision comes down to risk and probability. What is the probability that 3I Atlas is extraordinary enough to warrant a dedicated mission? Most scientists would put that probability low, perhaps a few percent. But a few percent chance of confirming that an artifact from another civilization is passing through our solar system is not a negligible probability. It might be enough to justify action. As of now, no mission has been approved or funded. The discussions are ongoing, the proposals are being evaluated, but the timeline is short. If a decision is not made soon, within weeks or months, the opportunity will pass. 3I Atlas will be too far away, moving too fast, for any realistic intercept to be feasible. This is one of the frustrating aspects of the situation. We have the technical capability to investigate this object more thoroughly, to send instruments close enough to resolve ambiguities that cannot be resolved from Earth-based observation. But we must decide whether to act based on incomplete information, knowing that waiting for more data means the opportunity will be gone. After December, when the object has passed Earth and begun fading, that decision effectively makes itself. If we did not launch a mission by then, we are committing to learning only what remote observation can tell us. That might be enough, it might not be. We will not know until the analysis is complete and we see whether the mysteries deepen or resolve. Chapter 918. The philosophical implications. Whether 3I Atlas is natural or something else, its passage through our solar system forces us to consider questions that extend beyond science into philosophy. What does it mean to encounter something from beyond our solar system? What does it imply about our place in the universe? And how should we respond to ambiguity, to phenomena that we cannot fully explain? If the object is natural, if all the anomalies turn out to have mundane explanations, it still represents something profound. It is material from another star system, formed under conditions potentially very different from those in our own system. It carries information about how planetary systems develop, about what gets ejected during formation, about the diversity of environments around other stars. Every interstellar visitor expands our understanding of the galaxy in ways that cannot be achieved by remote observation of distant star systems alone. But if the object is something else, if there is any truth to the hypothesis that it might be designed, the implications are difficult to overstate. It would mean we are not alone. It would mean intelligence exists elsewhere in the universe, intelligence capable of creating artifacts that function over millions of years and cross interstellar distances. It would mean that somewhere, perhaps long ago, perhaps still ongoing, there is a civilization that chose to explore the galaxy, that sent probes outward to study other star systems, including ours. This is one of the oldest questions humanity has asked. Are we alone? The search for extraterrestrial intelligence has proceeded for decades through radio searches, through searches for artificial signals in astronomical data, through studies of exoplanets looking for biosignatures. All of these efforts have come up empty so far, but they are searching for active, communicating civilizations. 3I Atlas, if it is a probe, might represent something different. An artifact from a civilization that is silent, distant, or perhaps long extinct. A probe could be millions of years old. The civilization that built it might no longer exist. Stars live for billions of years, but civilizations might be shorter lived. If a society builds probes and sends them out into the galaxy, those probes might outlive their creators by vast spans of time, continuing to function and explore long after the builders are gone. We could be observing the emissary of a dead civilization, a message in a bottle thrown into the cosmic ocean ages ago. This is speculative, but it is grounded in the same observations that motivate the scientific study. If we take seriously the possibility that 3I Atlas might not be entirely natural, we must also take seriously what that would mean. And what it means is that the universe is not empty, that intelligence has arisen elsewhere, that the exploration of the cosmos is not unique to humanity. There is also a more unsettling implication. If probes from other civilizations are passing through our solar system, how many have we missed? 3. I-Atlas was detected only because we happen to have telescopes capable of spotting faint objects and tracking their motion precisely. A few decades ago, we would not have detected it. The previous 2 interstellar visitors were found only in 2017 and 2019. We are only just beginning to develop the capability to detect these objects routinely. If 3I-Atlas is extraordinary, how many extraordinary objects passed through undetected in the centuries or millennia before we had telescopes? How many are passing through right now that we are missing because they are too faint, moving too fast, or aligned in ways that make them difficult to spot? The sobering possibility is that interstellar visitors, whether natural or designed, are more common than we realize, and we have been blind to them until very recently. The philosophical implications extend to how we think about evidence and certainty. Science demands high levels of proof before accepting extraordinary claims. This is appropriate. It protects against error and prevents premature conclusions. But it also means that ambiguous cases, phenomena that are unusual but not definitively proven to be extraordinary, tend to be explained away through natural mechanisms, even when those mechanisms require adding layers of improbable assumptions. 3. I-Atlas sits in this ambiguous space. Every anomaly can be explained naturally if you are willing to accept that unlikely things occasionally happen. But at what point do accumulated unlikely things stop being coincidence and start being evidence of something real? There is no clear threshold, no bright line that tells us when to shift from skeptical to convinced. Different people draw that line in different places based on their prior beliefs about how likely extraordinary phenomena are. For those who believe that intelligence in the universe is rare or that interstellar travel is impractical, the threshold for accepting that 3I-Atlas might be designed is very high. The natural explanation will always seem more plausible, no matter how many unlikely assumptions it requires. For those who believe intelligence might be common, or that advanced civilizations might explore the galaxy, the threshold is lower. The anomalies might be sufficient to warrant serious consideration of alternatives. This is not a question science alone can answer. Science can tell us what the observations show, what the probabilities are, what explanations are consistent with the data. But deciding how much weight to give to low probability hypotheses involves judgment, and judgment is influenced by philosophy, by worldview, by how we think about our place in the cosmos. 3. I-Atlas forces us to confront these questions whether we are comfortable doing so or not. It presents us with ambiguity and asks us to decide how to respond. Do we dismiss the anomalies and move on? Do we acknowledge them but assume they will eventually be explained naturally? Or do we take seriously the possibility that we are observing something extraordinary and adjust our investigations accordingly? There is no right answer that applies to everyone, but there is value in asking the question, in being willing to consider possibilities beyond the familiar, in maintaining enough intellectual flexibility to be surprised by what we find when we look carefully at the universe. Chapter 20, December 15th. On December 15th, 2025, at approximately 14:22 Universal Time, 3I-Atlas will reach its point of closest approach to Earth. In that moment, the object will be moving at approximately 67 kilometers per second. Relative to the Sun, it will appear as a faint smudge in telescope images, magnitude 15 or 16, depending on current activity levels, far too dim for naked eye visibility, requiring moderate-sized telescopes even to detect. Its coma will extend perhaps 100,000 kilometers, with a faint tail streaming away from the Sun, barely visible against the background star field. From our perspective, it will cross the constellation Virgo, moving steadily toward the region of sky that contains the galactic center. Within weeks, it will fade below the detection threshold of most ground-based telescopes. Within months, Only the largest facilities will be able to track it. Within a year or two, it will be effectively invisible, lost in the vastness of space beyond our ability to observe. That moment, December 15th at 1422, represents the culmination of 6 months of anticipation, study, and careful observation. It is the point where 3I Atlas passes nearest to our world, where the geometry provides optimal conditions for observation, where we gather the last high-quality data before the opportunity vanishes. But the moment itself will be unremarkable from most perspectives. There will be no visible event, no dramatic phenomenon, nothing you could point a camera at and capture for posterity. Just an object in space following its trajectory as it has been for millions of years before humans existed, and as it will continue to do for millions of years after we are gone. The significance exists only in context, in the questions surrounding this object, in the data being gathered, in what analysis might reveal in subsequent months. The moment passes like any other, distinguished only by our attention and the meaning we project onto it. December 15th will come and go. Most of Earth's population will have no idea anything occurred. Those tracking the object will note the milestone, file their observations, begin analysis, and 3I Atlas will continue its journey outward, carrying whatever truths it represents beyond our reach. In the end, that is what December means. Not dramatic revelation, not definitive answers, but the point where we stop gathering new data and begin working with what we have. Where active observation transitions to analysis and interpretation, where the story of 3I Atlas as an unfolding event becomes the story of 3I Atlas as historical record. What we learn from that record, whether it confirms the natural explanation or reveals surprises that challenge our assumptions, will not be clear until months after December passes. The data must be analyzed, cross-checked, debated, peer-reviewed. Conclusions take time to solidify, longer still to reach consensus. But December 15th represents the end of the observation phase. After that date, we are working with what we managed to capture while the object was close enough to study. No second chances, no do-over. Whatever questions remain unanswered after December's data is fully analyzed will likely remain unanswered indefinitely. That finality shapes how researchers approach the observations. There is pressure to be thorough, to gather every possible measurement, to ensure nothing is missed that might later prove significant. But there is also acceptance that some questions simply cannot be answered from remote observation alone. We will know what we can know, we will not know everything, and we must make peace with that uncertainty. December 15th, 2025. A date that might become historical, the moment humanity observed its closest confirmed encounter with an interstellar visitor, or a date that will be forgotten. Just another observational milestone in the catalogues where thousands of other solar system objects are documented. Which it becomes depends entirely on what the data reveals. 3I Atlas might prove to be exactly what most astronomers expect, a large, unusual, but ultimately natural comet from another star system. The statistical improbabilities will be explained as coincidences that seem significant only because we were paying attention. The mass will be reconciled with composition through better models. The trajectory alignment will be filed as one of those unlikely but not impossible occurrences that happen occasionally in a large enough sample space. Or it might prove to be something that defies easy categorization. Not obviously artificial, that would require unambiguous evidence like geometric structures or radio transmissions. But strange enough that natural comet does not quite capture what we are observing. An object that raises more questions than it answers, that leaves researchers debating interpretation without reaching consensus. Or, with vanishingly small probability, it might prove to be something that forces us to reconsider our assumptions about what exists in our cosmic neighborhood. Something whose characteristics cannot be explained through natural processes alone. Something that requires acknowledging the possibility, however uncomfortable, that we are not looking at debris from planetary formation, but at a product of intentional design. We do not know. We cannot know until December's observations are complete and analyzed. And even then, we might not know with certainty. astronomical observation rarely provides absolute proof, only varying degrees of confidence in competing interpretations. What we can say is this: 3I Atlas represents an object unusual enough that careful investigation is warranted regardless of ultimate conclusions. Its mass, trajectory, timing, and chemistry place it at the boundary of what we consider ordinary, making it worth studying thoroughly to understand whether our models of interstellar objects need refinement. The December observations will provide the final high-quality dataset. What we learn will shape how we approach future interstellar objects, as they are discovered in increasing numbers over coming years. And somewhere in that data, in the images and spectra and measurements being gathered even now, lies information that will either reinforce our understanding of how the universe works, or challenge it in ways we have not anticipated. That is what December offers. Not certainty, but data. Not answers necessarily, but information that narrows the range of reasonable hypotheses. Not revelation, but the possibility of being surprised by what we find when we look carefully at something genuinely unfamiliar. The closest an interstellar visitor has come to Earth in recorded history. What it means depends entirely on what it is, and what it is depends on paying attention carefully enough to recognize the truth when the evidence reveals it. December will tell us what we need to know if we are watching closely enough to see it. The rest is just waiting.